Hi, welcome again to magnetism. Let us continue our discussion of the magnetic needle deflection. What we actually do here is we place a conductor. Here no current is flowing, and in this case of current is flowing like that. That is, the electrons are moving in this direction, but the direction of current is taken as that. Then the a compass is placed over the conductor and no deflection is seen here, and the needle deflects like this here and like that when the current was in this direction. Why is that? Let us explore. Here when no current was flowing, the only magnetic field that was affecting this compass needle magnet was that of the earth. Okay, and since the geographical North Pole points in the direction of the Earth's so-called magnet South Pole, North Pole would be attracted to South Pole. Therefore, this needle points in the direction of North Geographic Pole or Earth's magnetic South Pole. Okay, since unlike poles attract each other. But when a current flows through it, the conductor, mm, then there is not only the Earth's magnetic field affects it, but also the field caused by the current affects the needle. How does it do? Well, by this law here, or the hand rule here, when we place our thumb in the direction of current, the fingers curl around the direction of magnetic field lines, the tangent to which would be the direction of magnetic field. So when the current flows like this here, the field would be actually like this, and the compass is placed here. Okay, when the field is like this, say in this direction, well, actually in a bar magnet you can see that the field lines go towards the south pole. So here also, since the magnetic field is like this in this direction, it will for the compass needle, it will actually feel as if there was a south pole here. Okay, a south pole here, so that the field lines go into the south pole, uh, like in this. Okay, so this is the north pole, this is the south pole, and therefore they attract each other, and the compass needle points in this direction. It won't be completely horizontal, since there is some portion of Earth's magnetic field as well, which tends it to align in this direction. So actually it would be in the mediatory of the two directions. Okay, when the current flows in the opposite direction like this here, then the field pattern would be like this, going like this. So when the compass is placed like over the conductor, the field would be like that in this direction. Okay, so it would the compass needle would actually feel that there is a south pole. Remove this. There's a south pole here, therefore the north pole of the compass needle gets attracted to the assumed south pole, and therefore it points in this direction. Hope it helps though. What I mean by the compass needle feeling as if there was a south pole is that the effect produced by uh, a south pole of a magnet placed here and the field produced by the current going in that direction is equivalent, since the field pattern is the same. Okay, so that is it. Our knowledge so far can actually help us understand the field pattern of a solenoid and why this is the south pole and that is the north pole. Okay, when we see the field pattern of a bar magnet, we see that the field lines go into the south pole and come out of the north pole. So actually if we can prove that the field pattern is like this, that is going into from here and out from here, we can say that this is the south pole and this is the north pole. How do we do that? Well, we can use the corkscrew rule to determine the direction of the field line. Let us do it. Uh, this is the battery, this is the positive terminal, and this is the negative terminal. Conventional current direction is from the positive terminal to the negative, like this. So current flows like this and like this here. So apply the corkscrew rule at this point. Current is going like this in the downward direction. Therefore, the field pattern would be a circle like this, which would point actually in this direction, in the inside of the solenoid, and in that direction in the outside of it. But since this is the field line of the inside, when the current is going down from here, so the field would be going in this direction. And we can actually apply the corkscrew rule to any part of the solenoid. Consider the point from when the current is coming here, here, going backside, and coming here and going in this direction. When the current is going in this direction, the field pattern would be like this. But no, like this. Wait. Oh, sorry, let me do that again. Yeah, when the current is going like this, and like this, that is when it is coming. These are the loops, and when it's coming in this direction, the field would be like this, the pattern. So therefore, again inside the solenoid, the field would be in this direction. Therefore, we get this line here in this direction. But you may think that uh, the screw rule says that if we have a conductor, then the field lines are total circles like this. Then you might think that why the field pattern doesn't look like this: circles here, circles here, circles here, and so on. Well, the reason is that we don't have a straight conductor. We are applying the rule to infinitesimally small part of the loop, which can be treated as a straight conductor. So each small part contributes to the field. So actually the field at one particular point is the sum of the fields caused by all of these parts. And so when we sum actually all those contributions by the different loops and the different parts, we get this pattern. Okay, uh, so this is how the pattern would be. And as a quick review, well, in the south pole, uh, here the current was flowing in this direction like this, and in the north pole it was going in this direction. Okay, so let's apply the rule here. Current like this, so field lines going into this, okay, like this. And when the current is going in this direction, you can see that field lines will come out of this north pole. Hence the field pattern would be like this, and therefore we call this the south pole where the field lines go into, and this the north pole where the field lines come out from. Hope it helps. Thank you, and please watch the next video. In the next video we actually discover deeply how magnets work.